In this video, I'm going to show you how to set up a problem involving a moving mesh to simulate a fluid with a free surface. So this is the simulation already set up. What I did is to insert a physics like this. So I went to component and insert physics, and using this one, fluid flow, two-phase flow, moving mesh, laminar two-phase flow. So selected that, and when I did that, I get this physics here, the regular laminar flow node, but I also have this modification here. So if you look under definitions, you have this moving mesh node is inserted when you select this physics. And so what's happening is that you have the regular laminar flow physics, and it's being modified by this mesh that moves according to how the definitions that are described here. So let's just take a look at this. I guess I don't really have anything set up here under global definitions in this problem. None of this stuff is being used. So come down here to the moving mesh node, and the default is that it's a deforming domain. And if we right click on moving mesh, you can see we have a variety of selections here. So deforming domain is going to be the default. So this is our geometry. This is a tank, and there'll be an outflow point on the tank right here. So we need to specify that the mesh can slip along these sides because the tank is going to drain out this point right here, and it will the mesh will collapse down in this direction. So let's put a mesh slip along those four boundaries, or along those two sides. We should also be able to have mesh slipping here, but I don't think that's really necessary because this free surface here on the tank will move downward. So this mesh here on the bottom shouldn't slip. So that's the only setup that we have to do for this problem, for the deforming mesh. Now, if we go to geometry, this rectangle that you can see, it's 2 meters wide and half a meter high. And I just put a point here, right there, at along this side, 1/10 of a meter up, and that's going to be the outflow point. So material, I'm assuming this is water, and the laminar flow physics is set up like this. The default, these nodes here are defaults, and we're just going to use the density of water and viscosity. Initial values is just the default, and we'll override the wall. So when I set up the laminar flow, I checked off the include gravity, and that got this entry. I'm just going to use a constant gravitational acceleration in the y direction. And this is going to be important here. I added this right here under two-phase flow moving mesh, the external fluid interface. So for this problem, this surface here is the external fluid interface. And I'm assuming that the pressure here is 0, atmospheric pressure. And if I expand it out, I'm going to put in I added this. This is the boundary condition. And this allows the boundary to move. U and V are the components of the velocity in the x and y direction. and nx and ny are the normal vectors, normal to this boundary. I put in surface tension. This is a fairly big problem, so surface tension won't really be all that important, but I included it. And the mass flux at this interface is 0. We could include a non-zero mass flux, for example, if we had evaporation. So for the wall, I had the wall boundaries. I had a slip boundary condition that's a little more forgiving than the non-slip, and we're going to want to have the fluid slip along this boundary as this interface moves down. And then at the outlet, I just specify the pressure, and I'm going to compensate for hydrostatic pressure. I'm just going to hold the pressure here equal to 0. The mesh, this is just the default mesh, and the study also is the default study. So we can go ahead and run this. So I'm plotting the pressure here in color, and you can see the mesh. In this particular plot, this is a wireframe plot, and so we're seeing the mesh here deform as the plot, or as the simulation executes. Okay, so we let it run for 2.5 seconds of simulation time, and on my computer that took 1.5 minutes. And this is the plot that we've been watching. It's also, I think, of interest to plot, to do a mesh plot. So I made another 2D plot, and I did this. I selected the mesh plot here, and that's going to give me this plot here at 2.5 seconds. And what's showing here is the quality of the mesh elements. And so what we can see is as this mesh gets deformed, these elements that were mostly equilateral triangles become deformed, and the mesh element quality decreases. The best quality is green, and then you decrease as the color gets warmer. So you can see some of these elements that the quality is getting worse. And if we were to run this out a little bit longer, the mesh element quality would continue to decrease, particularly right around here. So that's something you should try. And I also did animation. This is what this simulation looks like. And you can see as we open this valve, this would be a fairly large valve in this tank, we get this wave being produced, and it migrates down the length of the tank and reflects back. So that seems reasonable for the kind of physics that would occur in this kind of a scenario. So this shows you how to set up this problem of a moving fluid boundary that is tracked by this moving mesh.